Now we introduce energy-based learning. In a regular reinforcement learning, for given state, we need to optimize the model parameters set to find the optimal action, which can produce minimum loss along a trajectory. Alternatively, energy model-based model evaluate a configuration constructed by state and a possible action to evaluate, to calculate the energy for the configuration, see which configuration can produce the minimum energy. From the minimum energy, we get the model parameters. Classification problem in machine learning is to find the probability of a possible label condition on an input X. Energy-based model measures the capability of between the input X and each possible label Y using the energy function E, Y, X. Gibbs distribution is original from physics. It's used to evaluate status of a physical system. Right now, we use the Gibbs distribution to connect the system energy with the conditional probability. For example, here, this is a Gibbs distribution. Here E is the energy, the beta is inverse temperature, X is the input, Y is the label. This denominator is the partition function. When this integral is a convergence, then this gives the distribution equal to the conditional probability. For example, in the traditional classification in the machine learning, we give X, we train the network, find a better label. But right now, we evaluate the configuration constructed from X and Y. See, which configuration can produce the minimum energy. Then we find the model parameters. In the classification problem, we use the energy-based model to find the best label minimum this energy by selecting probable Y. This Y is a set of label. Suppose the training examples is a data set include p pairs of training examples. It's X is the input, Y is a label, and W is model parameters. So the trainer energy-based model can be expressed in this form. This is a loss. Here is a model parameters. This is the training example pair. Consider the regular rider W, or we have the following. This is just like a minimum constraint problem. We can route it to the Lagrange. We get this formula. We get this equation. This equation is for all the examples in the training data set. For each, the loss for each training example, we use Gibbs distribution. We get a negative log likelihood loss, and this way, take this Gibbs distribution. We take a log, negative log. We got this formulation here. This part is a free energy. B, the beta is a positive constant. This is for general case. For the before examples in the training data set is independent. That means ID, and here this conditional probability expressed in this way, and then the original problem can be simplified using the chain rule, here, because it is independent ID, so we can express this as the multiplication of each conditional probability. If we use you apply the maximum likelihood estimation, we can find the optimal distribution of W and minimize the negative log of equation above here. You see, I take a log, and here then we can change the multiplication to the summation. And again, if we use Gibbs distribution, and when then it's a log, take a log, two parts, one part is numerator, one part is denominator. And then because we use maximum likelihood estimation, that means you see this already we use more training data, we get better performance. We get better performance because the performance improved with the increase of the training examples. So finally, we get a negative log likelihood is here. This is a formulation for this loss function for the classification. Next, let's see what about the regression loss function. Suppose this is GW, X is a regression function, the energy function defined by this way. And it's the this discrepancy between the output of the regression function and the answer Y. Because if energy is minimal, so this answer, this Y equal this regression. So the minimum energy is 0. So the free energy in the free energy here is 0. 0 means we can get the a loss function is only in the this energy for each example, and we put all the examples together by using the maximum likelihood estimation, and then we get this discrepancy. This is the loss function. So how can we calculate, the further express this loss function? We need suppose give suppose G is a linear function, for example, in a popular way. G is a linear function of a parameter, capital Phi, and then we get this regression as this summation, and here then we substitute this regression function into here. We get the final formulation for the regression loss function to get the optimal model parameters. For more detail, please check with the reference here. Thank you. Bye.